So probability, that's what we're starting with today. So let's take something like a coin flip. Everybody's familiar with a coin flip. And so I'm going to flip a coin. I have two possibilities, heads or tails. What kind of language do you use when you're talking about a coin flip? You say, you know, I have $1 million on the line. It's going to come down to a coin flip. What kind of words do we say?
50-50.
We say things like 50-50. Do we say things like that? Yeah, everybody understands that. 50-50, stuff like that. What does that mean? Well, the 50-50 actually in this case refers to percentage. 50% one way, 50% the other way, but more importantly, it's equally likely. Now, if I have dice in my hand, are all outcomes equally likely? You know, the sum being 2, or the sum being 12, or the sum being 6, you know, maybe, maybe not. I have a deck of cards, and I'm going to deal them to you, you know. We're playing poker. Are you going to get some fantastic hand dealt to you? Yeah, maybe, maybe not. More likely you got a bunch of random cards in your hand. So we're going to talk about how do you calculate the probabilities, okay? Somebody actually said something to me. They were watching one of my videos, and they said, you don't have your mask all the way over your nose, you're going to get in trouble. I said, no, actually, I'm more than 6 feet away from everybody. Mm-hmm. There is no mandate, but you guys are within 6 feet of each other. That's if you guys know this, every time I've walked up to you, what do I do the moment we talk? Every time. Why? Because I'm being considerate. I'll leave it at that. We don't, it's not really useful anymore, but we got to do the right thing. Because I don't want anybody coming by. People don't do that, but yeah, we've had people do that. They get nasty. So probability is a number that measures the likelihood. Now here's the one thing people don't understand. It doesn't mean it's going to happen. How many here watch sports, even mildly? Okay. Does anybody watch tennis? Okay. I watched tennis yesterday. And I'm a big tennis fan. I'm a big Roger Federer fan, but Roger's pretty much done. But the big three for the last literally 15 years, Djokovic, Federer, Nadal, and they basically win everything every time. It gets kind of boring. There was a match yesterday between Nadal and an American, Tiafino, I think was his name. I'd never heard of him. He had never even won a set off Nadal. If you were a gambler before the match, and you had a chance to bet on that match, if you were a gambler, who would you have bet on? Nadal. The guy who's won more majors than anybody in the history of the world, or the guy who's never even won a set off of him? That's kind of a no-brainer, isn't it? If you got a chance to, you bet everything you got. And did anybody watch that match? The American kid destroyed him. He destroyed him. I don't dislike Nadal, but I always root for the Americans. That's me. You know, I root for the Americans. You know, if Serena wasn't an American, I'd make an exception. But because she's American, it makes it even easier, right? I root for the Americans in those kind of matches, but he destroyed them. Now, gamblers would say, but it was a sure thing. Well, actually, the probability that Nadal should have won was very, very high, but he still didn't. So what do we call that in sports?
Odds?
Well, no, when the one who we didn't think was going to win wins. What do we call that?
An upset.
That's called an upset. Can upsets happen? Of course upsets can happen. And that's why gambling can be so frustrating for people. You bet on the sure thing and the upset happened anyway. But the point is, if you understand probability, then you go, oh, okay, it's rarely a done deal. It's rarely certain that something's going to happen or not going to happen. So we start off with the following. There's a few words I got to introduce before we can talk about probability. First thing is called the experiment. Now, I don't mean you're in a lab with a bunch of beakers that are smoking and you're mixing chemicals. The experiment is what you're going to start measuring. My experiment might be, I want you to roll the dice and add up the numbers. The experiment might be, I want you to flip a coin 10 times. Okay? The experiment might be, I want you to shuffle a deck of cards and pick one card out of the deck. That's the experiment. Okay? Now, a lot of times we know the probability of something before we actually do it, like a coin flip. Okay, like a dice roll. We actually know the probability ahead of time. If we know the probability ahead of time, then we call it theoretical. Okay, because I already know that. You know, I'm flipping a fair coin. I already know it's going to land heads half the time. I didn't have to flip it 1,000,000 times to figure that out. Does that make sense? But there's a second type of probability. Okay? The probability that somebody wins the game. Or let's say, I want to measure your free throw shooting skill. I don't know what it is, so what's the easiest way to do it? Watch you shoot a bunch of free throws. And see how many you make. So that is after the fact. That's called experimental. The one where you know ahead of time is typically, think of the coin flip, the dice roll, the cards. That's ahead of time. Some of you may have heard this term before. How many have ever heard the term a priori? It's Latin. It just means you have prior knowledge. It means you already knew the probability before you started. The other one is, I have to actually see it happen. Okay? So let's just say we're in an arm wrestling contest. You're an arm wrestler. And I don't have any idea how good you are. So I watch you do 100 matches. And you won 60 of them. Then can I say, I think you're going to win about 60% of the time. Would that be a reasonable conclusion? Yeah. But did I know that before I saw you arm wrestle? Couldn't have known that. You had to do it ahead of time. I want you to flip a coin 100 times. I think you're going to have about 50 tails. Why? Because it's a coin flip. It should be about half tails. I don't even need to see you flip the coin to know that. Now, you found in your backyard, I don't know how it got there, one of those Roman denarii, that were around, the Caesars and all that. Do you think that's equally likely to land heads and tails? No. I guess not even probably round, I have no idea because of the weight and all this. It might land one side way more often than the other because of the weight, just the imbalance. In fact, it's probably not completely flat and certainly not circular and perfectly. So you'd have to flip it a whole bunch of times to figure that out, wouldn't you? So we wouldn't use prior knowledge in that case. So the experiment we start with is usually something easy that we can easily measure, like a coin flip. So the experiment, we clearly label what it is. Then we have something called the sample space. A lot of you have heard that term, perhaps. The sample space, think of it as a list of every possible outcome of your experiment. Okay? The sample space is everything that could happen. Now, if it's a small experiment, I can actually write down the sample space. If it's a large experiment, it might take me a little, it might be a little bit different because a lot of this involves counting things. Okay, so the sample space is every possible outcome. So if I said to you, I want you to flip a coin 10 times. Oh boy, there's a lot of outcomes. Tails, head. If I start writing them all down, the heads and tails, that would be a large number. But what if I said flip a coin 2 times? Flip a coin 2 times. 2 coin flips. I want to make this simple. What would all the possible outcomes be? Well, it'd be heads followed by heads, heads followed by tails, tails followed by heads, tails followed by tails. Is there any other possible outcome I could have if I flipped the coin 2 times? So this would be my sample space. Now, what is it you're measuring the probability of? I don't want to just write down a sample space and walk away. I want to know, well, what's the probability that the following thing will happen? So the next thing is the event. The sample space is every conceivable outcome. The event is the outcomes you are particularly interested in. Okay, here's what I want you to do. I want you to flip a coin 2 times and find out the probability of getting no tails. How many of these outcomes have no tails, by the way? Only this one. So my sample space was all 4 of these outcomes. My event was this one particularly. I might say, flip a coin 2 times. I want to talk about getting at least 1 tail. At least 1 tail. Well, that's at least 1. That's at least 1. That's at least 1. So these 3 outcomes would be my event, wouldn't it? Okay. So the event is what you're measuring. So the event is usually smaller than the sample space. But one thing the event can't be is bigger than the sample space, can it? What you're measuring can't be bigger than what it is you actually expect. I'm going to flip a coin 2 times. My event can't involve 3 or 4 or 5 coin flips. It can only involve 2 coin flips. So now we want to count. Often the sample space is listed as a big S. The event is listed as a big A. We'll often use capital letters like A and B for the event, just to be consistent. We typically do things the exact same way. So notation-wise, the number in S the number in A. This means the number of things in S, the number of things in A. It's just brief. So in this case here, what would be the number of things in my sample space? How many outcomes do you see? 4. So NS would be 4. So now we can define formally what probability is. The probability of event A occurring is, and the notation we often use is this, just to make it easy. Capital P of A, in English, the probability of A occurring. Yeah, we like to abbreviate things and then always do things the exact same way so nobody can possibly misread. This is equal to the number of things in the event divided by, what do you think? The number of things in the sample space. So probability, by definition, is a fraction. Now, let's go back to this example over here. You flip 2 coins. Let's call the event A at least 1 tail. Okay? Then how many things are in A? We just said that a moment ago. 1, 2, 3. Agreed? How many things are in S? 4. So if I ask you what is the I'm going to flip a coin 2 times. What is the probability that I get at least 1 tail? Anybody want to answer that?
75%.
Never give probabilities a percent. Give probabilities a fraction. If it makes sense to convert it to a decimal, you will. You never give probabilities a percent. Because people hear percents and they think large numbers. Now, in English, you can say, oh, it's 50% likely to occur. That's fine. But when you're doing a calculation, never use a percent because you're almost always going to be using that value again. And you don't want to be converting back and forth. People get in trouble. So what's the answer?
3/4.
3/4, that's it. 3/4. If it makes sense to convert it to a decimal, it's 0.75, which is 75%, but probability is not defined as a percent. Percent has nothing to do with probability. Probability is defined to be this fraction. This fraction is not a percent, it's just a fraction. Now, do we agree that the sample space ought to be bigger than the event? I want to flip a coin 2 times. What's the probability that it landed heads or tails each time? Well, of course it's going to land heads or tails. What's the probability? Well, I just made my event the entire sample space, didn't I? So what is the absolute largest number of probability could be?
The sample space.
No, but in terms of the probability, if my event ended up being the entire sample space, then what is the value of this fraction?
1.
1. So the probability of A has an upper limit of 1. I'm going to flip a coin 2 times. What's the probability that I get struck by lightning in the process? That's pretty much not going to happen. Do you agree? I just gave you an event that was impossible. I gave you an event that has no outcomes. Meaning my numerator is what? 0. So what would my quotient be in that case?
1.
If that's 0, what's the quotient?
0.
0. A probability must be between 0 and 1. Is that kind of an ODA? Hopefully. If you're asking something that's impossible, it cannot happen, then the probability is 0. And by the way, do things like that happen all the time, that the probability is 0 of something happening? Yeah. Yeah. There's a lot of situations where the probability is 0. You're going to get in your car and you're going to drive across the parking lot. What is the probability that you just drowned in the ocean during that process? You'd say, well, I'm pretty sure that can't happen because I'm driving across the parking lot. So that'd probably be 0. What's the probability that you're going to reach the other side? There's nothing wrong with your car and there's nothing in the way. I'm pretty sure that's going to happen, so that's a probability of 1. I'm being silly here. If it's absolutely impossible, the probability is 0. If it's absolutely certain to occur, then the probability is 1. And almost everything is probably somewhere
in between.
in between, okay? It's pretty unusual to ever have something to get a 0 or 1, but understand those are the extremes. So I just asked you for the probability of something and you gave me a really large integer, really large number. Is that a possible answer for a probability? No. Probably what you just did was you gave me the numerator or the denominator of the question. But if I'm asking you the probability of something, it cannot be a large integer, right? It's got to be a quotient. Oh, so I might say, how many things are in this event? How many things are in the sample space? That might be a large number. Okay, let's do another problem, really similar problem. All right, I'll do a coin flip again. I want to flip a coin 3 times. Now, when we talk about a coin, it's sort of understood, but it's not automatic. You hear the term fair coin, okay? And it's almost an absolute, and when I put this in writing, I'll always use the term fair coin. It sounds redundant, but what do you think it means when you say a fair coin?
Equal chance of landing on both sides.
Great answer. The heads and tails are equally likely. Okay, does anyone here know what a Harvey Dent coin is? I love using that example. It's one of the Joker Batman movie. Anybody ever remember that one?
Yeah.
Harvey Dent had a special coin.
It's my head on the sides.
Yeah, he'd say, I'm going to flip it, and the fate, you know, whether I shoot you or not, is going to depend. And it was heads on both sides. So pretty much, yeah, you were in trouble if he said, you know, heads I shoot you, tails I don't, but it was heads on both sides. That's a Harvey Dent coin. It can't land tails ever, can it? So that's not a good coin to use in this environment. A fair coin is one that's absolutely equally likely to land, and that usually has to do literally with weight distribution when the coin's made. Is it possible you could have a coin that is more likely to land heads than tails or vice versa? Yeah, you could make it in such a way that it was just heavier on one side, and that's not good. How many ever watch NFL games in general? Okay, they're going to overtime. What do? They do a coin flip to see who gets the ball first. Do you know that the NFL actually keeps statistics on the coin flip? And do you know which side lands more often than the other since they've done coin flips? By the way, there are thousands and thousands and thousands of, they have a lot of, big database. So they have all the overtime games that have ever happened and they have the database. Do you know which happened? It's not equal. It's not exactly 50-50. Does anybody know which side? There's an expression that they use. Anybody know what it is? Tails never fails. That's an expression that I've even heard the announcers use. Always pick tails. It's over 52% of the outcomes have been tails. But it's supposed to be completely random. But for whatever reason, that coin that they use may not be equally weighted. So you're the person calling the coin flip, call tails. Because it does land tails more than half the time. That's why that's the expression they use in football. That, by the way, don't do that in life, but in football, because they're using not a regular just coin that you pulled out of your pocket. They, you know, one of these special design coins that's really huge and all this stuff.
So, like, would that actually be applicable, or is that just like a random chance? Like, for example, like the gambler's fallacy, where it's like people are like, oh, it landed like this very often. So
no, that's a great question. If I just grabbed a coin out of my pocket, it's probably equally weighted. This was a special coin they made just for the coin flips, because the other thing, you know, it's a really big coin, so you can see it on the camera. But because it wasn't minted by the US government, it was minted by the NFL, that coin is probably not perfectly balanced. And now, it might be, but the fact is in thousands of coin flips, tails have landed far more often than heads. So, if it were a perfectly balanced coin, then it wouldn't make any difference. But you're right, you hold that thought, because that's going to come up often. He used something called the gambler's fallacy, and I'm going to talk about all these things, because everything's mathematical and fairly simple conclusions. So now, a fair coin. If I say fair dice, that's something that actually is a real thing. If it's not fair, there's an expression. Anybody know what the term is called? If the dice are not fair. A fair die means it's equally likely to land on any of the 6 sides. An unfair die means it's far more likely to land somewhere because the weight distribution has been purposely altered. That's called loaded dice. Have you ever heard the term loaded dice? Loaded dice are dice that are not properly balanced, and you know ahead of time what the likelihood is, and therefore the probabilities change drastically. It's cheating. It's basically just simply cheating. Loaded dice. So we use the term fair because we don't want to worry about that. You know, that somebody's not only trying to cheat us, but that I can't calculate things if it's not fair. It's too much physics that have to go into it to figure out the new probabilities. I want to flip a coin 3 times. I want to find the probability of, how about, exactly 2 tails. Okay? So my experiment is 3 coin flips. My event is exactly 2 tails. So what I need to do is write down, first of all, and I'm doing this only because it's a really small problem. I can do this. I'm going to write down every possible outcome I can have with 3 coin flips. Heads, heads, heads. Heads, heads, tails. Heads, tails, heads. Heads, tails, tails. Tails, heads, heads. Tails, heads, tails. Tails, tails, heads. Tails, tails, tails. I'm kind of systematic in my approach to make sure I don't miss any. How many outcomes do you see there? 8. Could I have known 8 ahead of time, by the way? That there would be 8? How many outcomes, by the way, if I flip a coin 1 time, how many outcomes are possible? 2. If I flipped the coin 2 times, how many outcomes were possible?
4.
If I flipped it 3 times, how many outcomes?
Oh, okay.
8. Anyone want to go out on a limb on 4 coin flips? 16. How does that be? Because after each of these, I could have put a head or a tail. After each of these, I could have put a head or a tail. And what did that do? That doubled the next round. And after each of these, I can put a head or a tail, which will double. It just keeps doubling. Oh, is that useful to know that? Yeah. Because then I know the size of the sample space without actually having to write it down. I'm going to flip a coin 20 times. Yikes. I don't want to write that down. Well, why not? Because it's over 1 million. But I can tell you exactly how many there are. I just need a calculator in my hand. Ooh, 2 times 2 times 2 times 2. Okay. Now, this is my sample space. Let's call the event that I want exactly 2 tails. So event A, and by the way, usually the way to do it is I'm going to put comma, dot, 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 comma, last one. This is the formal way of doing it. I actually list them side by side. Okay? And I'm going to ask you a question on a quiz where I'm just going to say, write down the sample space. And you just write this or this or this or this or this. Okay? So in other words, this, comma, this, comma, this, comma, this, all the way down. My event, therefore, are which outcomes? Well, let's see. I asked for exactly 2 tails. Which of these outcomes have exactly 2 tails? I think it's this one, this one, this one. Did I miss any? Or are those the ones? Okay, so my event would be HTT or THT or TTH. My sample space had exactly 8 outcomes. My event. The event is the thing I actually want to count, which was, I wanted all the ways you can get exactly 2 tails. That was my event. So now I can say, the question was, find the probability of exactly 2 tails. So what is the probability of A? And I'm being lazy. I could write, what is the probability of getting exactly 2 tails on 3 coin flips? That's a lot of writing. Since I did 3 coin flips and my event was getting 2 tails, I'm just going to call it probability of A. Anybody want to try it?
3 over 8.
3 over 8. That was easy. Because you're counting. You're not calculating. A lot of times probability is nothing more than a count. Later it will involve calculation because there's going to be large values that I have to actually need a calculator to calculate. I didn't need a calculator for this problem, did I? I just counted. We like to start that way because it's easier to understand. The probability of getting exactly 2 tails in 3 coin flips is 3/8. By the way, what's the probability of getting no tails? Can you tell me that, looking at the picture?
1/8.
The probability of getting no tails? Well, don't one of these outcomes have no tails? But only one. Oh, so what do you think the probability is? 1/8. So let's make a little table here. Okay? My outcomes called number of tails, all right? I can get 0, 1, 2, or 3. Now, how about the probability? Well, we just did 2 tails and you said it was 3/8. Okay. I asked what's the probability of 0 tails and you told me it was 1/8. All right. How about all 3 being tails? Would that also be 1/8? That leaves one more. What's the probability of only getting 1 tail?
3/8. 3/8.
3/8? Okay. That's interesting. Anybody notice anything about the right-hand side?
Adds up to 8.
Adds up to
8.
1.
It adds
Oh,
up to 8,
Oh,
Yeah.
1. Yeah, because it's 8 over 8, right?
which is
1.
1. It adds up to 1. Is that a good thing? It's kind of important. We just broke it down. We flipped a coin 3 times, calculated the probability of basically every conceivable outcome, and those probabilities added to 1. That's a good thing, isn't it? That means everything's covered. So if I flip a coin, I got to get something in there because everything's been covered. Probability cannot exceed 1. Now, if my numbers added up to greater than 1, then we probably have a problem. If my numbers added up to less than 1, we probably have a problem. I probably miscounted somewhere. Is it possible to miscount if we're not careful? Sure. If it were a really big problem, it's easy to miscount. So I don't want you to worry about that. I just want you to notice that we just covered every conceivable outcome and it added up perfectly. That's a great thing. So probability is simply the number of ways the thing you're interested in happened divided by the number of possible things that can happen all together. And that's kind of a loose, simple way of doing it. So when I flip a coin 1 time, it's really easy, right? There's only one way to get a head, or there's only one way to get a tail, but there were 2 possible outcomes. That's why each of them is 1/2. That's where the term 50-50 comes from. Okay, now I have a single die in my hand, right? A die has 6 sides on it. I have a single die. What do you think the probability of each individual outcome is? Which would be a 1, a 2, 3, 4, 5, or a 6? Anyone want to take a guess on that? What would be the probability? You're going to roll that single die. What's the probability you get a 3? 1/6. Does that make sense? Oh, that makes sense, because I have 6 possibilities, and if it's a fair die, most important, they're all equally likely to occur. That's kind of huge, by the way, the whole equally likely to occur thing. Okay? So I want to talk about rolling the dice, because rolling the dice is an interesting thing. A lot of folks have a misconception about dice roll. Every time you roll the dice, the numbers that show up, every possible combination of numbers is equally likely. But don't you add the numbers when you roll the dice? Right? When you're all done, don't you, you're playing Monopoly, don't you add the numbers? I have a 4 and a 6, don't I add them and say I just rolled a 10? So if I add them, do things change? Yes. I'm going to give you a dice roll chart. I'm giving you every conceivable outcome if you roll the dice. Because this will make it easier for us to explain what the heck's going on. This is every possible outcome if I roll the dice. Okay? Now, when you roll the dice...
Wait, you can have 7. Doesn't it start at 7?
There's no 7 on the die. There's only
Yeah,
1
but
through
you
6.
can roll a 6 and a 1.
Well, that's a sum.
What are those?
These are the numbers on your dice.
Wait, what?
What?
You have 2 dice in your hand. Each die has a number 1 through 6. 1 through 6. You roll the dice, you see a 1 and a 1. You see a 5 and a 2.
1 and a 1, 2. Okay, I see.
Oh.
You have a 3 and a
I thought
4.
that was 11. I thought that was.
Oh, no, no.
Yeah.
These are the number on your dice.
Okay.
It says every possible set of numbers. Now, I want to add them up because when you're playing, right? Do you play any games where you're only looking at the individual? You rolled the dice and you're only looking at the numbers? No, you always add them up. I mean, let's face it, dice roll games, you add them up. That's not a big deal. Okay? So I've got a situation. I rolled all the dice. Every one of these outcomes is equally likely. But now I'm going to add them up. And we might see something slightly change when I add them up. All right, what are the possible sums I could have? Well, what's the smallest sum you could have?
2.
2. What else could you have?
3.
3, 4, 5, 6, 7, 8, 9, 10, 11. What's the biggest possible sum you get?
12.
Do we agree that you can't exceed 12 when you roll the dice? And you can't get less than 2. Do you agree that every one of these sums is possible when you roll the dice? Now, how many possible dice rolls? Not sums. How many rolls are possible? In that grid, just multiply. I have more than 3
36.
pairs written up there. How many pairs do I have?
I thought you said
36.
There's 36 pairs up there. So when you roll the dice, not sums, just looking at the numbers on the dice, there's exactly 36 things that can happen. Okay? 3, 4 is different from 4, 6, and 5, 2, and 1, 1. There's 36 things that can happen. Now you're going to add them up. Okay? But my point being, the probability, since there's 36 possibilities, every one of these numbers has, or every one of these outcomes has a probability with a 36 on the denominator, because my sample space has exactly how many elements? 36. That's what we just did. My sample space has exactly 36 outcomes. So every one of these probabilities has a denominator of 36. Now, how many ways can I roll a sum of 2? How many ways can I roll a sum of 2? Just one. So is a sum of 2 highly likely when you roll the dice, or is it like the least likely? It's like the least likely. Oh, what do gamblers call that particular outcome? Anybody know?
Snake eyes.
Snake eyes, because that's what they look like on you. Snake eyes, there's only 1 out of 36 probability of rolling snake eyes. Then let's go to the other extreme. I want to roll a total of 6, or excuse me, a total of 12. Would you agree that that's the only way I can roll a sum of 12?
Yeah.
So what's the probability that I roll a 12? 1 out of 36. Okay, we'll see if you really understand the gambler's language. What's a double 6 called? Anybody? You guys know snake eyes, boxcars. Which, again, that's a stretch, I know. Snake eyes is easy. You know, they look like snake eyes. Boxcars, they look like train cars, side by side. I wasn't there when they decided that. Now, how about if I want to roll a total of 3? A sum of 3. Would you agree it's those 2 right there?
Yeah.
So what's the probability that I roll 3? 2 out of 36. I'll use orange here. Huh. Well, while we're at it, how about a sum of 11? How many ways can I roll a sum of 11? 2. I just circled them. So what's the probability that I roll 11? Would you agree it's 2 out of 36? Can I calculate the probability of every one of my sums? Yeah, that's not very hard to do. I just got to count. Are we calculating or counting?
Counting.
We're counting, which is way easier, but only if a list is short. If you've got a bazillion things in your list, you're not going to count them. It takes too long. Now, do you notice how easy this is? Those are all the 4s, aren't they? So the probability of a 4 is what? 3 over 36. Let's keep going. What's the probability of a 5? Oh my gosh.
4.
4 over the... I think some of you might even see a pattern here. Okay, let's go out on a limb. Sum of 6?
5 out of 36.
A sum of 7. How many ways can I roll a total of 7? It looks like there's 6 ways. So 7, 8, 9, 10, do I just keep going?
Go back 10.
Or does it start going the other way? Why? Because it starts getting less. So what's the next one?
5.
5. Then what's the next one?
4,
And the next one.
3.
And then you already told me 2. Oh, now, add those probabilities together. By the way, you can be lazy. You know how you can be lazy? Add the numerators. 1 plus 2 plus 3 plus 4. Well, that's 10 so far. 15, 21, 26, 30, 33, 35, 36 over 36. Is that a good thing? Means I did it right. My probabilities add to 1. So dice are actually really easy to work with. Now, what kind of gambling games involve dice? One of the oldest ones.
Craps.
Craps. That's one of the oldest games of chance there is. Craps involves dice. Now, craps is not a game that I ever played. I don't like it because it's the probability of winning is not good. But the idea in craps is you're looking for certain outcomes. I'm going to give you the Reader's Digest simplified version of craps. You're playing craps, you roll the dice. Okay? And what you get is called your point. Now, as long as you don't get a 7 or an 11. If you get a 7 or 11, you lose right off the bat. Okay? So, let's say you rolled a total of 6. Let's just say that was your total. Now you're going to roll the dice until either you roll that or you roll a 7 or 11. But if you look at 7s and 11s, there's 8 ways I can roll a 7 or an 11, which is a higher probability than any other outcome, which means you're going to lose far more often than you're going to win. But can you still win? Could you roll your total of 6 before you roll a 7 or 11? Sure. Yeah. I mean, the dice don't remember what you just rolled. They're not conspiring against you. But your probability of winning is probably not great because what causes you to lose is a lot more likely than what causes you to win. And you're going to play until you either get the winning number or the losing number. That's the overly simplified version. But that's a game of chance that people have been playing for years and years and years and years because all you need is a pair of dice. You don't need anything else. You don't need any props. You don't need any poker chips. You don't need any equipment. You just need dice. So that's what craps are. Okay? So that's a game of chance that is very, very common. That's not the only one. It's not the only game of chance. Okay? Can you do me a favor? Let's go ahead and open up the back. I think we've lost the cold nature of the room that we started with. So if somebody could just prop a chair open back there. Because with the doors closed, or that door closed, we're starting to suffocate a bit. I see a lot of nodding heads. Yeah, unfortunately, there's no fresh air coming into the room from that door. All right, so this is a fairly simple notion. Again, if I know what my sample space is, then I just count it. Any chair. Oh, you're going to take that. That's why you take that one.
That's it.
Yes, probably less effort than the other one. Now, what if I ask you for more than one thing? I have 2 things that are going to happen. I want either, this outcome or this outcome to happen. So, I'm going to draw a picture. This is what's called a Venn diagram. A lot of you have seen Venn diagrams in the past. I have 2 events. Call it event A and event B. Keep it real simple. I'll be really generic. I love Venn diagrams because they're a really simple visual over what it is we're actually trying to measure. So if I asked you for the probability of event A, then you already know what's going on. I take every outcome that's in A, count it up, and let's call the whole thing my sample space. And I just do that quotient. If I said, what about the things in B? Same thing. But in my picture, is it possible that I got overlap? Do we have outcomes that potentially could be both A and B at the same time? In my picture? Yeah. Yeah, if you were here, you're in both. There's a name for this area right here. This is called the intersection. You guys remember that? And we indicate that as A intersect B. So you remember that from ancient history. Now, what if I said I want to include everything here. Doesn't matter if you're an A or B, I just want to include everybody here. Then what's that called if I take the entire thing? It's not intersection, there's another word that usually goes hand in hand. Remember? Union. I want everything. And that we usually write this way. That looks more like a U, so that's easier to remember. Now, here's the thing. Keep it really simple. I teach a Calc 3 and a linear algebra course this semester, and there are a lot of students who are actually in both classes. Okay? So I'm going to have a party next weekend, and sorry guys, your party is the weekend after. But I'm going to invite everybody in those two classes. So let's keep it really simple. Let's say I have 30 people in each class, and then I have 10 people that are actually in both. Let's just keep the number simple. All right, so I'm going to send out invites to every single person in my two classes. And let's say everybody decides to come. So I have 30 in one and 30 in the other. So I'm going to have 60 people show up, right? You're shaking your head. But there's 30 in one, there's 30 in the other, and everybody's coming. Why won't there be 60?
There's an intersection.
Because there are people that are in both classes. Okay, so let's make it real simple. Let's say that, let me go back to this. I want to keep this really simple. I just said, let's say this is my Math 252 class, and let's say this is my Math 254 class. So I have 30 people here, I have 30 people here, and I have 10 people in the intersection. Is this an accurate picture?
No.
No, because now aren't I saying that I have 40 people here? Oh, if there's 30 people in the A circle and there's 10 in the intersection, then what number should I be writing right here?
20.
Not 30. 20, because does that make sense to you? Oh, so how many should be here? Also 20. What are these 20? These are the people in 252 only. What are these 20? 254 only, and who are these 10? Both. Are there 30 people in the A circle? Yep. Are there 30 people in the B circle? Yep. So if I wanted to invite everybody and everybody comes, am I going to have 60 people? No, I'm going to have 50 people. Because I would have counted these people twice, and that would not be good. So when there is an overlap, which by the way is probably more often than not, when there is an overlap and you don't take that into account, you will always overcount. So in terms of probability, you will be too much. And so I'm going to show you how to do that. Okay, let me erase this. It's a really simple thing. So I want to find the probability of A or B, which basically means union. I have two events going on, and I want to find the probability that either one of them happens. It's real simple. It's equal to the probability of A plus the probability of B. Piece of cake. Except that if I have an overlap, I just counted them twice, didn't I? So what did you do? You shook your head right off the bat. You said, no, it can't be 60, it's got to be 50. Could I have said 30 plus 30 minus 10? In a sense, would that have been easier than trying to break it down 20? That's probably easier, wouldn't it? To go 30 plus 30, but I double counted the 10, minus 10. You add them up and you subtract the intersection. That's it. This ensures that you won't count those people twice, because the intersection was already in A, the intersection was already in B. If I don't subtract the intersection, then I counted them twice. And if I count them twice, then I'll have an incorrect count. So I'm going to give you a very, very simple example of this. All right. I went out yesterday and I did a poll of San Diegans. Okay, I love doing polls of San Diegans. All right. With football season coming up, you know, a lot of people do polls of San Diegans. So my San Diegan poll, what do you think it'll involve since football's coming up? Probably something to do with, do you hate the Chargers? That's usually what most polls are. I have fun with that one. Okay. All right, so let's say that the two questions that were asked, Charger fan. How about, what would another good one be? Sunshine fan. Both. So I went and randomly asked San Diegans, are you a Charger fan? You said yes or no. Do you like the sunshine? You said yes or no. If you said yes to both, you're a both. Agreed? But I went around and asked people, are you a Charger fan? And let's just say hypothetically that, and I'll put down percentages, 50% of the people in San Diego said they were still Charger fans. And I said, how many of you are a fan of sunshine? Let's say 90% said they were a fan of sunshine. Now, how many of you are a fan of both? Let's say that was 45% said they were fans of both. You like sunshine and you like the Chargers. Is that possible you could like them both? Is it possible you don't like either one? So let's make a Venn diagram of what I just said. Okay? So this will be Chargers, sunshine. And instead of percent, we'll put decimals because probabilities usually are decimals. So tell me if this is right. 0.5, 0.9, and 0.45. Is this a correct and accurate picture? How do you know it's not right? There's a really easy way to know that. Because if you add up the numbers, it's bigger than 1. By the way, folks, if that one doesn't hit you over the head like a ton of bricks, oh, when I add up those numbers, they add up to more than 1. Yikes. By the way, do those 3 numbers have to add up to 1? No. They have to add up to 1 or less. Why? Is it possible, I said, do you like Chargers? No. Do you like sunshine? No. Are there going to be outcomes where they said no to both? Yeah, and by the way, those folks I just simply put them out here. Oh, so those numbers have to add up to 1 or less. So I'm going to show you the trick to making this work. You always start with the intersection and then work your way out. 50% or 0.5 are Charger fans. Well, I've already counted for 45% of them right here, so how many people should be out here?
0.05.
0.05. Why? Because this has got to add up to 0.5. Now, this circle has to add up to 0.9, but I already got 45% of them here, so it should be another 45 out here. Now, does that add up? By the way, what do these add up to so far? 0.95. That's 95% of the folks. So, the folks you don't want to hang out with, right? They don't like Chargers or sunshine. Gosh, what a downer, right? Now my numbers add up to 1. Do you agree? So if I said to you, what is the probability that somebody is a Charger fan, but they hate the sunshine? Can you tell me that number? You're a Charger fan, but you hate sunshine. 0.05? What's the probability you love the sunshine, but you hate the Chargers? What's the probability that you love the Chargers or you love sunshine? What do you think?
90.
That would be all of this, wouldn't it? Does everyone see that? And what is that number, by the way? 0.95. Now, could I have gotten that number from these numbers here without drawing a picture? Yes. It would have been the probability of Chargers, which was 0.5, plus the probability of sunshine that was 0.9 minus the intersection. And that is our 95. I could have gotten it by just using this simple formula here, or by drawing the Venn diagram. I love the Venn diagram, but simply writing out the formula would have been faster, wouldn't it? But the picture often makes it really clear what the heck's happening. What is the probability of finding someone who doesn't like either? It's right there. Do you agree that there's nobody that's excluded here? Every person is represented here. You like the Chargers and don't like sunshine. You like sunshine. You don't like Chargers. You like the both. You like neither. Everybody's up there now.
So 0.5 plus 0.9 minus 0.45 isn't 0.95.
Yeah, it is.
How?
Well, use a calculator if you're not sure.
Oh, is that a 4? Is that right?
959.45. You just said it out loud, so. So this plus this minus this, in a sense.
Yeah, but you wrote 0.95 as the answer.
The answer is 0.95. 0.5 plus 0.9 minus 0.45 is 0.95, which is the same as we would have gotten here. Now, again, the Venn diagram is a great visual. You don't ever have to do it to answer the question, but a lot of times it makes the answer make more sense to you. That's why I like doing it.
So it's okay to write that 90% are fans there, but it's not okay in the Venn.
Well, I'm sorry.
So right there, you're right that there's 90%, right?
Oh, but I'm saying, what percentage, because I start by saying, what percentage of San Diegans are this. But when I do my calculation, I need to use decimals, not percentages, because probability is not a percentage. But if I said, what percentage of the people, think of an opinion poll. How do you usually say something? This percent of the people think this way, because that's English. We understand that. So when I want to do the mathematics and start doing the calculations, I just simply need to convert that to a decimal in order to do my calculations. Now, will I get a different answer? No, but if I said, what is the probability, you'd say 0.95. If I said, what percentage of San Diegans, you could say 95%. Are you saying the same thing?
No, so what I'm saying is that you wrote 90% here, right? But 90% is technically misleading, right? Because it's actually, then you're adding the both and the Sunshine fans, right? So it doesn't make sense. Like the Charger fans should be 5% and then...
No. Careful. I start by saying, do you like the Chargers? You say yes or no. You're tallying now as a Charger fan. Do you like Sunshine, yes or no? Now I'm telling you, and I say, oh, he was a both. Let me keep that track. I don't now remove you from either group. But I said, oh, you fell into the intersection.
But in the Venn diagram, you do that. Like you change
right,
it.
Because there's my 90%. There's my 50%.
So why don't you just do the same for there, though?
Well, it's too much work if I say, are you a Charger fan? Yes. Are you a Sunshine fan? No. Are you a Charger fan and not a Sunshine fan? Are you a Sunshine fan and not a... Too many questions. I just want yes or no, but I can ask multiple yes or no's. If you say yes to everything, then you're in the intersection. And I just keep that also. How many said yes? That'd be kind of like my example where I had two different classes. I said, are you in 252? Yes or no? Yes, I am. You're in 252. Are you also in 254? Yes, I am. Okay, you're in the big circle, but I'm going to count you in the intersection. But you're still in this circle. I don't somehow remove you from that class because you're in both. I put you here if you're in both. I put you here if you're only in the first one. Does that make sense? So that's why I keep account of both at the same time, just so I know what my intersection is. Is it possible that there's no intersection? So in a group like this, let's suppose I stratified you, keep it real simple, by age. How many here are 21 and over? How many here are under 21? Can you be in an intersection? No. Is it possible we could have a scenario where there's no intersection? Yeah, actually, if I stratify, I really don't want intersection because I want each group to be completely separate. I could say male and female. I could say over or under. I could say citizen, non-citizen. I mean, there's a parent, non-parent. Do you agree? I could ask a bazillion different questions where you're in one or the other, but you cannot be in both. Do you agree with that? What do we call it when there's no intersection? And by the way, that is very common also. What do you call it when that means there's no intersection? We say in this case that these events there's two words we use. Disjoint. Disjoint means they don't overlap. That's a picture thing. Or we say the events are, and you probably have all heard this used in common language, mutually exclusive. People use this in everyday language all the time, and usually incorrectly. Mutually exclusive means you're talking about two things that cannot simultaneously occur. It's impossible. It's impossible to both occur. Now, if you have something that's mutually exclusive and you're saying both occur at the same time, there's actually a mathematical formal definition of that. There's a word, it's called contradiction. Contradiction is when you're claiming something and two things are both happening that cannot possibly happen at the same time. It's impossible. You cannot be over 21 and under 21 at the same time. And if I include you in both groups, we have a problem, right? There would be a contradiction there. So that's not something we want to do, because that means a mistake has been made. I don't want to go that route. It's like, no, we want to do things correctly. So if I'm mutually exclusive, this formula still applies. It's just this quantity would be 0. So in the case of the dice roll, are there any outcomes of 4 that are sums of 4 that are also at the same time sums of 5? No, every one of these would be completely disjoint, wouldn't it? A total of 4 and a total of 5 are completely separate things. You can't have them both occur at the same time. Does that make sense to you? Yeah, okay, that makes perfect sense. By the way, I want you to roll the dice. I want your sum to be even. What's more likely, an even sum or an odd sum? Ooh, that's a tough question. Well, how would I know? Which sums are even? Well, there's more even sums. So let's count the even sums. 1 plus 3, that's 4. Plus 5, now I'm up to 9. Plus 5, that's 14. Plus 3, that's 17. Plus 1, that's 18 over 36, which is 1/2. So what are you more likely, to be odd or even in your sum? Or is it exactly the same? It's exactly the same. Isn't that kind of cool? The probability of an even sum is exactly the same as the probability of an odd sum, because you just simply counted them and added them together. I didn't have to worry about this because there's no overlap in these sums. That makes things easy. Now, how many have played the game of Monopoly at some point in your life? I would be surprised if a hand doesn't go up. Did you know that Monopoly is absolutely entirely based on probability? The entire game is probability. How do you know that? Because what dictates everything in the game? Dice roll. So did you know there are actually strategies that you may not be aware of? Strategies involved that increase your likelihood of success, winning. Success we'll call winning. There are bad strategies and there are good strategies. Now, I love using Monopoly because everybody's played Monopoly. It's governed by the rolls of the dice, and most people think it's completely random. It actually is not. It's actually entirely predicated on wise moves and unwise moves. So let me give you an example. I haven't played Monopoly in many, many, many years. I used to play when I was younger. But I have the Monopoly board deeply embedded into my brain. Go. What's here? Jail. What's here? Free parking. And what's here? Go to jail. Yeah, okay, everybody knows that. Now, the most commonplace, sorry, I can't, that looks like a jack. Jail is actually, in the game of Monopoly, the single most landed on space. Did you know that? That's interesting. Because you can pass by it or you can be sent there, and there's so many ways. So, the question is, we're playing Monopoly. Do you know what is the highest probability color group that you can land on? I'm not going to fill in the whole board. What is the most people don't realize that. Now, what goes, everybody knows what's right here. Boardwalk. Everybody wants Boardwalk and Park Place, right? But they are the least landed on properties in the entire game of Monopoly. Therefore, they're the worst properties to own. Second worst of these guys. The most valuable properties to own are the reds, but the most landed on properties are the orange. Now, okay, this is bad, okay. There's New York, there's Tennessee, there's Community Chest, and there's St. James. This is 6, 7, 8, 9. It's always 10 across.
What about, there's some cards that say like, go to,
And that increases the probability of getting there. That's true. So, When I was about 10 years old, I read a book called 1001 Ways to Win at Monopoly. And it was a mathematical book. It was entirely based on probabilities. And by the way, this is a million years ago, so whoever did this, computer technology, you had to understand, was pretty raw. So it took a lot of calculating. But they calculated the probability of reaching any particular property, starting at any particular property. And so doing computer simulations and all these things, they figured out what is the most likely landed on place, what all of these things, and then all of these different strategies. I read it, I started following it, and then I never lost again. In fact, if we played Monopoly, the game never lasted more than about 10 minutes, believe it or not. I was going to beat you 3 times around the board, the game was over. So how could you? You know, and I don't mean stuffing money under free parking when no one's looking. I don't mean cheating. I mean, there are certain strategies that you can do that you don't even realize because they're built into the rules. But one of the things you do is you buy everything. You buy everything. If you got a mortgage, you got to buy everything. You can't win if you don't buy everything. And then wheel and deal, get your color groups. But if I got this and I got these, you had one more turn at most around the board. The game was over because the probability of missing them entirely was very low. If you're on jail, what is the probability that your next roll you're going to land on an orange? You can now tell me that. This is how Monopoly works. Now, what's the probability you're going to roll a 6?
5 out of 36.
5 out of 36. What's the probability you're going to roll an 8?
5 out of 36.
Sorry, where's 8? Oh, I'm sorry, also 5 out of 36. And what's the probability you're going to roll a 9?
4.
4 out of 36. So what's the probability you're going to land on an orange property if you're sitting on jail? We'll add those 3 numbers, and what does that come out to be?
14.
14 out of 36. That's just under 0.4. In other words, of all the places on the board, almost half the time you're going to land on the oranges. You might miss them, but you might not next time around. Or maybe you're starting from here next time around from here. Now, if you're here, what's the probability you miss this entire corner? It actually is very low. So the idea that everything is based on probabilities, but if it's a roll of the dice, I can actually tell you what the probability. So here's one of the strategies that I learned to use, okay? I have developed my properties. You know what that means? I put houses or hotels on them. You're sitting on jail. You're in bad shape. You're going, oh my gosh, if I land on them, things are not going to go well. So I'd say, all right, give me $500, I'll let you pass. But in other words, I'm selling insurance. Not only is that legal, that's one of the smartest strategies you can possibly do. I'm going to sell you insurance. You give me $500, I'm going to let you pass free whether you land on them or not. So if you do land on them, you don't have to pay me. But you said, but I might not land on them. That's how insurance works. You might not get into an accident, right? Now, I need one more of these guys to complete my color group, but I'm over here, and you're right here. I'm going to give you $500 for the right to buy that property if you land on it. And you're like, yeah, I might not land on it. I get to keep the $500, but if you land on it, then I get to buy it. That's legal. It's strongly encouraged. Those are the strategies I use. And the third one that nobody knows is you can't put hotels on a property unless there are enough houses to build one at a time. You also cannot remove your hotels unless there are enough houses to go down one at a time. So I never put hotels. I buy all the houses. It's called creating a housing shortage. It's the absolute guarantee that I'm going to win the next time around. Because if you have hotels, you can't remove them because I bought all the houses. So you have to deal with me. You landed on something, you only owe me a couple bucks, but you don't have any cash? Okay, I'll take that color group from you. You know, that's worth $1 bazillion because you can't pay your bill otherwise. Doesn't that sound hysterical? That's one of the smartest strategies. And when I was reading this book, I read this book, and many more books came out after it. This is not a joke. This is not a political statement. It was actually referred to in the Monopoly books, if you go back to the early 80s, it was referred to as the Donald Trump syndrome. Not President Donald Trump, real estate investor, entrepreneur Donald Trump. He had billions of dollars in real estate, but no cash. And he had to actually literally sell off or give away huge hotels to pay smaller bills because he had no cash. That's exactly what's happening in Monopoly. So it actually was given a name That's how he made his bazillions. It was on real estate and things like that. But the point is, Monopoly is a game entirely based on probability. What's the likelihood of the next thing on your dice? Which is kind of cool because now you know exactly, all right, I need to get double ones in order to accomplish my thing. But double ones are really unlikely, aren't they? Oh, but if I had to get a 6, 7, or an 8 to accomplish my thing, that's highly likely. So as long as I know that, I can make good decisions. So that's kind of cool, isn't it? It's kind of fun. So that's probability. Start with, if you have the experiment, what's the sample space? And we're going to start with simple things of that nature. What's the sample space? Now that I have the sample space, whether I list it or I just simply know how to count it, it's going to be the case really soon that I'm going to show you how to count it, and the counts are going to be large numbers that we need a calculator for. Now, what is the event that I'm interested in? That's basically the numerator. The sample space is basically the denominator. Once I do this, I have probability. Now, understand that all investing works with probability. But way bigger than investing is insurance. Did you, how many here have life insurance? Anybody have life insurance? Okay, what are your rates based on? Do you know? It's a real, loosely. It's based on what's the probability you're going to reach your next birthday. Literally is. So if, let's say you've just got insurance, you love skydiving, especially without the parachute, because you saw, Captain America, Winter Soldier, that's so cool. So you like riding motorcycles without a helmet, in other words, you have a lot of really dangerous habits. Is your life insurance going to be cheap? Probably not, because your risk is higher. So by the way, if you have life insurance, one of the first things they do, they come out and do a full physical, blood test, everything before you get insurance. You have a terminal illness and you want to get life insurance. Guess what? You can't. You can watch the commercials, they're lying to you. You can't get life insurance if you have terminal illness. It's not, unless you want to pay $1 million for, no, you can't get life insurance if you're not going to live very long. So they want to know, are you going to reach your next birthday at the very least? Now, if you're 20 years old, your life insurance is going to be a lot cheaper than if you start at 60. Why? Probably going to live a little longer, unless you have crazy habits. So life insurance is based simply on what is the probability you're going to live to your next birthday based on your health, your habits, your age, all of these things. And it is mathematics. It's called actuarial science. There are people, this is what they do. Now, investing is real similar. That your retirement accounts and all this, money is constantly being moved around based on the probability or the likelihood of success of that particular investment. Do they know if an investment's going to succeed? Well, they base it on recent history. Do we know if you're going to reach your next birthday? The probability all of you reach your next birthday is really, 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 really high. It's very high, unless right now you have something horribly wrong with you, right? You have a terminal illness. The probability you reach your next birthday is really, really close to 1. But is it 1 for everybody on Earth? Of course not. Now, you're 20 years old. Let's just say, and this is next day's lecture almost in a nutshell. You're 20 years old. The probability you reach your 80th birthday. What do you think? At least 0.5? Say you have healthy habits, good medical insurance. Maybe it's higher than 0.5 that you reach your 80th birthday. That's probably reasonable. Maybe it's 0.5, maybe it's 0.6. You're 79 years old. What's the probability you reach your 80th birthday? You think it's higher than the 20-year-old?
Yeah.
It's probably like 0.99. Why? Because you only got to go 1 more year. They got to go 60 years. They got to pass through all of the things that could have knocked them off along the way. Does that make sense? Oh, if I'm almost 80, the probability I reach 80 is going to be really, really high. If I'm born today, the probability I reach 80 is not that great because I got to live a whole life first. Now that should make some logical sense. Oh, okay, so it does matter how old I am today to say what. Now, regardless of your age, what's the probability you reach your next birthday? That's probably really high unless you have really, really dangerous habits. So all of that's based on probability. All insurance is based on probability. Sometimes it feels random to you. So why does the 16-year-old have so much higher auto insurance than the crappy driver 45-year-old? Yeah, but you know somebody in your family who's, older and they're probably a terrible driver. Yet their insurance is way cheaper than the 16-year-old. Why is that? What do you think?
Because they're like more mature. They're more likely to do dangerous
But
stuff.
you know they're a terrible driver.
Like they're in like a high risk group.
Yeah, the 16-year-old is just probability of an accident is infinitely higher than any other age group. Yeah, I always have fun with this because people always say, well, you know, boys are so much better drivers than girls. It's 16, it's not even a close call. Boys, I don't know the number, but it's several times more likely to get into an accident. I was a 16-year-old boy once. I was the best driver on planet Earth the day after I got my license, which, by the way, is sort of the universal thought process of all 16-year-old boys. No, I wasn't, by the way. So therefore, did I take chances that I probably shouldn't have? Yeah. Did I take risks? Did I have absolute control of the wheel? Probably not. So the point being, if I got unscathed those first few years, my rates probably weren't going to be terrible. But I don't know a whole lot of male drivers under the age of 21 that have a perfect driving record. Okay, we'll put it this way, I don't know any. Whether it's accidents or tickets. It's, you know, they have a very large collection, but it was never their fault, of course, you know. That's always the fun one, never their fault. But the point being, everything's based on probability. So once you understand a little bit about probability, you don't have to do the calculation, but then you can understand how things are arrived at, how are decisions made, right? What is the conclusion that we can make based on certain things? So if everything financial is usually based on probability, then if I know what probabilities are, then it will help me. These are things that we're going to discuss along the way. So today is just introducing this is what probability is. That's it. That's all it is. Okay? And then once we understand that, starting to do the simple calculations. So today we said, I have more than one thing happening. Oh, add up the probabilities, subtract out the intersection. Tomorrow or next day we're going to talk about what if I have more than one thing happening? I have this thing followed by this thing followed by this thing. We're going to talk about those rules. I'll give you a hint. They don't involve addition, they involve multiplications. And we're going to go through all of those. What if I have, you know, prior knowledge about something? Might that affect the probability? Actually, yeah, hugely. So we're going to go through every possible situation and rule, and it's kind of fun because it's not complicated, and a lot of it you'll say, that makes perfect sense, that's exactly what I thought it should have been. And a lot of the times the conclusions we make will be exactly the conclusion you would have come to before we even did it. We just show that that's the right thing. I'm going to give you a really simple example. If I flip a coin, a fair coin, 1,000,000 times, am I going to get exactly 500,000 heads and exactly 500,000 tails? That's virtually impossible, by the way. Because that's basically saying the coin has a little computer chip in it that's keeping track. Oh, okay, I got to go tails this time. I'm going to go heads. No, but you can say whatever outcome we get is probably going to be very close. Might be a few more, might be a few less. And therefore, you can actually talk about a range of values that you're probably going to fall in. Okay? But if I flip the coin over and over and over and over again, what I actually physically see. So we're going to do a simple example. I'm going to have everybody here take a coin and flip it 20 times and count the number of tails. What kind of numbers are we going to see? Are we going to see some 10s? Sure. Some 9s? Some 11s? Some 8s and 12s? Probably less of them. Some 5s? Maybe a 15 here and there? Sure. 0s and 20s? Probably not. But if I now said average all of the outcomes, you know what we'd see? Pretty darn close to 10. Would we see exactly 10? Probably not exactly, but probably really, really close. Some people have heard this term, the law of large numbers. Anybody ever heard that expression? The law of large numbers is the concept, if I take something where I already know the probability, and I do it over and over and over and over and over again, large numbers. What will I see? Exactly what I'm supposed to see. The law of large numbers says if you do the same thing over and over again where you already know the probability, then the outcomes you see should be exactly the outcomes you were expecting to see. Will I get exactly 500,000 heads and exactly 500,000 tails? No. No, but I'm going to be ridiculously close in the end. That's why. Okay? So that's why you can do certain things. Let's say from a gambling standpoint, if you know the likelihood of something happening, you can use that in your decision making. That doesn't mean it's going to happen. But if I kept doing that over and over and over and over again, what I would see, my final results should sort of mirror the probabilities that were already there. And that's actually comforting to know that, unless you're just really, really unlucky. Okay, all right, go ahead and stop recording.